So LeetCode 1026 maximum difference between node and ancestor. So basically in this problem you're given a binary tree and you want to find the greatest possible difference between a node and another node that is in its right or left subtree. So for this problem the brute force solution would be to just traverse the tree normally and keep track of all of the ancestors of your current path. So for example we would start from 8, then go to 3, and then for example we could go to 1 and say, okay, my ancestors are 3 and 8. And so then you try doing 8 minus 1, and then you try doing 3 minus 1, and you just take the biggest one and update some variable that you're later on going to return. But you can see that like intuitively, you can see that trying the difference between 3 and 1 is basically useless because you have an 8 here, which is greater than 3. So there is really no point in subtracting 1 from 3 since you have a bigger value anyway. And if you had like 1 here and 8 here, so if the values were swapped, then there would be no point in doing 8 minus 1. Sorry, there would be no point in doing 3 minus 1, where you have a bigger value, so you could just do 8 minus 1. So what this is telling you is that basically you don't need to keep track of all of the ancestors. You just need to keep track of the biggest and the smallest one, because all of the other ones are never going to make the biggest difference, because they're neither the minimum and neither the maximum. So there's always going to be either the minimum or the maximum, which makes a better pairing and makes a bigger difference. So yeah, we're just going to implement that intuition. So we're going to have a result variable, which we update with a recursive function, which I'll explain later. And then at the end, we just return the result. So this recursive function takes 3 parameters, which are the node that is currently visiting, and then the minimum value that we've found so far, and then the maximum value that we've found so far. And I've initialized those with the roots value, but you can also initialize them with like plus and minus infinity. So here's the implementation of the recursive function, which will update our result and keep track of the minimum so far and the maximum so far. So what you do first is your base case. So if you have no node, meaning that you went down an empty path, maybe you were in a leaf, then you just return, right? You don't want to continue recursing if your node is null. Then what we do is we update the minimum and the maximum so far with a simple formula. And then what you want to do is you want to call the recursive function on your left and on your right subtrees. Okay, so this is the basic idea of a recursive traversal of the tree. And now what needs to be added is the code that actually updates the result. So to do that, what we do is we compare the current node's value to the minimum so far and to the maximum so far, and we do the difference between them. And then we update the result with the maximum between the current result, and then the difference between the current node's value and the minimum so far, and the difference between the current node's value and the maximum value so far. Okay, so first of all, we calculate the differences. So this is the difference with the maximum value, and this is the difference for the minimum value. And then what you do is you update the result with the maximum between the result, the difference with the maximum value found so far, and the difference with the minimum value found so far. And some of you might be wondering why I do not need to do a math abs here. Like this could be negative technically, because like let's say that here I have 3 and then here I have 8. So then the maximum so far would be 3 and my current node's value is 8, right? So what I would do is I would do 3 minus 8, which would result in minus 5. And the reason for which I do not need to have a absolute value is because I do the difference with the minimum anyway. So there I would have 8 minus 3, which would be 5, which is kind of the same as having the absolute value there. So nothing of value is lost. We still have all of the information needed to return the correct answer. So I'll just submit the solution to show you that it works. And the time complexity here is O of n, because we go through all of the nodes once. And the space complexity is technically up to O of n if the tree is very unbalanced. So the space complexity is just the stack space for the recursion, which is O of height of the tree, which could go up to O of n. Okay, so that's it from me today. Thank you for watching and bye.